All. Oh, we are live now.
Okay, thank you, Asif. So, greetings to all the esteemed speakers, guests on the stage, and the co-chairs, and all the distinguished participants who have joined this session. This is the session three of the conference, and I am A.K. Mittal, associated with TSDSI as advisor, network systems and technologies, and I am the convener of this session. And you know that this conference is a 3-day conference, and yesterday we had the inaugural. Today we have the whole day assigned to 6G related deliberations, and this is the last session of the day, and we are going to discuss the topic of research trends in localization, sensing, and IRS. So these are the new areas which are emerging in towards 6G technology developments. And this session is co-chaired by Mr. Srinivasan from Nokia and Mr. Srinath from Lekha Wireless. But before I introduce them, there are some hygiene instructions for the participants here. The important point is to note that the mics, that means audio and video, is muted by default centrally. And if you have any question, please ask in the Q&A box. It will be attended appropriately at the time when the Q&A portion starts for each keynote. You would have seen from the agenda that after every keynote address there is a Q&A, and after the panel also there is a Q&A. So you can put your questions, and we will make best efforts to reply all of them with the limitation of time of the session. And the rest of the questions can all be can be replied by the speakers and the panelists in the box itself. And but there is a chat box also where the participants can chat among themselves. And please try to put questions only in the Q&A box so that we can handle as many questions as possible. And if you want to expand your screen, there is a four arrow, expanding arrow kind of sign at the right corner of the screen. You can push that so you can see more clearly. There is a, if you have a video problem or audio video problem, try to change from HD mode to the LD mode. On the bottom right corner, there is a HD sign. You can show to LD. And this hygiene instruction sign, this slide is being put in the chat box for your reference during the conference if you have any doubts on that. Otherwise, you can put a question in the question box also. We'll attend to your problem or advise you if any changes are required. So now coming to the introduction of the co-chairs. So as I told, session co-chairs are Mr. Srinath Ramnath from Lekha Wireless and Mr. Srinivas Silva Ganapati from Nokia. So Mr. Srinivasan is head of India standardization and also 3GPP Rank 2 delegate for Nokia with overall 20 plus years experience in cellular wireless industry and more than 10 years in standardization and research. As a part of standardization research activity, he has filed 200 plus patents related to cellular standards with 30 plus granted patents. He is an MS from BITS Pilani, pursuing PhD in the networking and communication from Triple IT Bangalore. His research interest is massive MIMO and cellular IoT. Next slide, please. Yeah, Mr. Srinath Ramnath is just a second, please. Mr. Srinath Ramnath has obtained his master's from Indian Institute of Science, Bangalore, and PhD from INRIA, France. He has about 3 decades of research and development experience in the wireless industry, working on various technologies including GPS, CDMA, wireless LAN, WiMAX, LTE, and 5G networks. Currently, he is Director Systems R&D at Lekha Wireless Solutions, Bangalore. He is a co-inventor of multiple patents and has co-authored numerous research publications in reputed international journals and conferences. He is a senior member of IEEE. His research interests span wireless communications, signal processing, networking, optimization, and game theory. So, with that introduction, I hand over to Mr. Srinath Ramnath for further proceedings. Thank you.
Yeah, I hope everybody can hear me. Thanks, Mithalji. Uh, Good evening. Welcome you all to this interesting session on research trends in sensing, localization, and IRS. Basically, like some of you who have been following up the day's activity would have seen that we had the focus topics have been on 6G. Basically, the first session talked about one of the key enablers, that is AML. In the second session, like we covered vision, interface, and network related things. So this session basically covers what we would call as three of the key enablers for 6G. Okay. So last few years, like maybe I could say like in the last 5 years, a lot of things have happened in these different areas, and these advances are going to be the like the key ingredients of the 6G technology, which is kind of going is planned somewhere maybe around 2026 to 28 time frame. Right? So we have here a distinguished set of keynote speakers and panelists who would be giving you an idea about these different technologies, giving their perspectives, some thoughts, future work, and what can be expected. So we have Ratnakar Rao from Samsung, Hideaki from Nokia, and Professor Azad, Arzad Alam from IIT Bhilai, who are the keynote speakers. We also have an interesting panel comprising of three keynote speakers. Plus, in addition, we have Professor Sandeep Chapuri, and then Vinay Srivatsa from Reliance, and we have Priyanka Dev from Civit. So I hope it will be an interesting session, and then there'll be a lot of takeaways. I welcome you all once again, and let's pass it on to Srinivasan to initiate the keynote session. Thank you, and have a good learning experience. Over to you, Srinivasan.
Yeah, good evening, all. So let's start the keynote sessions. So the first keynote session would be on the localization techniques towards 6G networks. So we have the localization techniques got very good attention in the standardization, even in the 5G NR, where there are already localization improvements on multiple aspects, even until 5G advanced. Now we will hear from our esteemed speaker, Ratnakar Rao, who is a senior director engineering at Samsung R&D, and he has over 22 years of experience, and he has specialized in wireless protocol, and his interest of area includes AI in wireless and next generation communication system. And he's also a senior member IEEE and has 20 plus international patent grants. And on that topic, he would touch upon the challenges of using NRAR interface in a reliable way for localization, and also the research efforts which is ongoing to optimize the 6GR interface jointly for localization and sensing, and touch upon the new use cases which would require the localization improvements. And welcome Ratnakar Rao sir for the keynote speak on localization for 6G.
Yeah, thank you very much, Srinivasan. So I guess I can proceed.
Yeah, sure, sure.
Okay. So firstly, a warm welcome to all the uh, other co-panelists, co-speakers, organizers, session chairs, as well as all the members of the audience. It's my pleasure to virtually connect with you all and exchange a few thoughts on this important area of the beyond 5G systems, which is the localization and sensing aspects. So I'll try to throw some light on what happened so far and what are the challenges. I mean, and what are we likely to encounter as we go beyond 5G, right? And how that shapes up the localization in the beyond 5G systems, and also the challenges therein. I mean, what the both the research community as well as the industry need to address, right? So I'm sharing my screen. Hope this should be visible to you all now. Okay. So Yeah, initially, I mean, what I realized is, there is a great deal of diversity in the jargon used across industry, academia, as well as the engineering practitioners. Because most of us, who are fed up on the GPS days of positioning, right? So actually refer things as positioning, identifying the location of a terminal uh, in a given network space, right? So, but whereas this, localization terminology is becoming very prevalent, especially I heard it's coming from the robotics parlance, right? Where in a given indoor environment or probably even outdoors, uh, a robot or a moving terminal has to localize itself where it is, in a given three-dimensional space, so that it can plan its movements and next steps or next actions. So in that sense, I mean, for the purpose of our discussion, I think I would like to, reusably use probably localization or positioning. But if we are very particular, then probably that's what is my, definition. I mean, of where localization is coming from. And now you add to this the extra dimension of sensing, right? It's like, then what is sensing? Like, if there is a positioning which is same as localization, where is sensing coming from? So that's where, I mean, we need to understand probably that it all depends on what are we trying to localize, right? So in case an anchor, like a base station or some network element, is trying to locate a terminal, so that's one kind of a localization, or right, or positioning. Or a terminal identifying it with respect to an anchor, identifying its own position, right? That's also another dimension. And now the third, irrespective of network, for example, if a given terminal, for example, it has to identify its own environment, using the RF medium, right? So that's what probably we can call it as sensing. So in that sense, if the target becomes passive, maybe broadly what we can call is, we are actually sensing the environment. Whereas if there is active assistance from the other party, the other party can be network or terminal, maybe there is an active target involved, right? That's how we can break that confusion. So then lastly, of course, I mean, traditionally, all the business of localization, of course, except for, barring the GPS terminals, it's all the function of, the in the radar scheme of things, right? Where you locate the objects in free space. It can be air traffic controller, it can be, weather monitoring or any kind of surveillance, right? So far, I mean, it was a separate discipline in that sense. I mean, compared to the traditional communication, where, the focus is always on how do I improve my spectral efficiency, right? Or how do I pump more data? How do I minimize my latency? All those things. So in that sense, I mean, various technologies, as we see, I mean, I have listed whatever on the top of my mind, uh, already try to do one of these things, right? They either try to actively localize or rather passively sense the environment. So that's where you can see these pictures. I mean, we have all kinds of, starting from the satellite assisted location versus, some kind of AI based sensing kind of a parlance, which we'll see going forward. So there are these all kinds of schemes. I mean, there are passive, active, network driven, terminal driven. So probably I would like to fit some of the existing techniques into this kind of a framework. This is how they fit in my mind, right? So it's important to understand this because the lot of techniques are already set, and they're actually working in various, use cases in various scenarios. So it's important to understand, I mean, what exactly 5G doing and where exactly we'll go in the beyond 5G space, right? So that's the context before we go forward. Yeah. So now in terms of localization techniques, I mean, so as we go beyond 5G, so what exactly is done so far? There is a great deal of diversity. So you would have seen, this picture where, starting from the cell ID based localization, which is a very, very, what should I say, very, very coarse granularity,
to a very very accurate, probably there are techniques available even in the using the Wi-Fi and Bluetooth measurements, where you can locate an object probably much more accurately indoors, right? So this kind of diversity is already there. So what 5G brought in extra, right? So this you can easily take a look from this table. So 4G already added some kind of a reference signals, right? Like, so there are positioning reference signals in the downlink and the sounding reference signals in the uplink, based on which a base station can accurately identify, where the device is coming from, by using the TDOA techniques. So this is kind of a network assisted way. So there is a downlink which the UV measures and sends it back to the network. And if the network has to figure it out on by itself, then there is SRS already provisioned in the standard. So on top of this, with this higher band spectrum and with all this beam management, MIMO techniques, so what 5G made possible is, I can actually go more for a angle of arrival methods. So that's what I try to capture here, where probably in the beam space, a device can identify, hey, in this 3D beam space, which beam index is whatever most suitable for me, and based on that, can I estimate the angle of departure from the base station? And the same thing probably network can compute using the angle of arrival, based on the uplink beam index. So, but other than that, if you see, all other techniques are actually independently evolving. So, like for example, most of our devices, probably if you are using a Samsung flagship or a Apple flagship, for example, so they already come up with some kind of a UWB sensor, right? Or there are actually sophisticated sensor hubs already available, right? And coupled with now, you have your Wi-Fi, Bluetooth, cellular, so you can capture all kinds of fingerprints and store, very complex databases, where the moment you see the fingerprint, match it with your database, and you'll be able to identify your location, right? So there are several proprietary databases already being built by storing the fingerprinting information of multiple radio access technologies. So then to top it off, of course, there are techniques like the Doppler shift based, especially for tracking, when you want to estimate the direction or the movement of an object, not just localize it, but track it as well. Right? So again, same thing. Network using the uplink reference signals or the terminal using the downlink reference signals can actually measure the Doppler shift independently, right? And can derive its own conclusions. So to me, probably, this is a gist of what we can call as the state of the art, right? Like what all possible till 5G or with 5G, right? So then the question comes, right? I think you would have heard. I think probably there is one table down below. If you see, I read it, taking it from this paper mentioned here. What kind of accuracies and latencies the 5G evolution itself is targeting, right? Even in release 16 or release 17, or in going forward in release 18. So already very high levels of accuracies are being targeted actually. So then, the natural question that arises is, so then what are those great or grand use cases which need capabilities beyond this, which need far more advanced capabilities than what is being currently planned, right? So that's where you'll see some of the new drivers, right? So there are drivers probably at a service level, right? A service can be, tracking a robot in an indoor environment, or probably tracking a drone in an outdoor environment, right? Or some, very precise XR kind of use cases, right? In XR, extended reality, you're wearing an XR headset probably, and even minutest of the minutest moments, in all degrees of freedom, should actually be trackable, right? And likewise, probably there'll be IoT scenarios like asset tracking, where you probably need to even detect a little shake to the precious asset what you're tracking or monitoring. But apart from that, forget any other user centric use cases. These are all services. Probably an autonomous driving is also a service, right? It's a commercial service. So forget all those use cases. Even the modern networks, 5G, beyond 5G, and the upcoming 6G networks need the positioning in a way to say for their own purposes, for their own RRM purposes, right? Because as we go to higher bands, we are realizing that okay, beam management has become a very very critical piece, and as we go towards probably upper millimeter wave or sub terahertz frequencies, so that it, it makes even more sense for the network to actually have a complete picture of its surroundings so that it can actually effectively manage its beams, right? And likewise, I mean, be it the traffic monitoring analysis, so basically to achieve all the network efficiencies using all the advanced sound techniques, which will be needed, especially because in the beyond 5G era, we are saying that humans are not going to be the main users. Machines are going to become the main users of the 6G networks. So, which means the network has to be much more efficient and accurate in dealing with them. So, from that perspective, I mean, you can see this table actually I tried to capture, right? Let's try to imagine, you know, what is the what is needed in a given technology to achieve accurate positioning, right? So, and then let's see, I mean, what 5G is already doing and what 6G promises to do, right? Or what's the promise of the beyond 5G. So yeah, the traditional positioning, what I mean, I'll send some narrow pulses. Probably I expect to capture as many reflections of my interest as possible, right? But for that, I mean, I need a higher bandwidth to capture all the reflections. So maybe your 4G did not allow that to happen, but with 5G mid bands and higher, right, and in FR2, so now you have a greater chance. Okay, you have a higher bandwidth channels available, and you have much more delay resolution, right? So now we all know like 6G is definitely trying to take this a step forward, right? Now we are talking about channel bandwidths greater than 1 gigahertz. We are now not only talking about upper mid bands or higher millimeter waves, but sub terahertz also is in the question, right? So which allows us to have a higher bandwidth channels and a very very, what should I say, accurate delay resolution. So then of course comes what I want, as many reflections, but at the same time I don't want a lot of clutter also, right? So I want to capture only the key features of my surroundings. So that's where probably we can imagine a sparse multipath. I mean, I don't need a cluttered multipath. So sparse multipath is another need. So which again naturally happens, nothing specifically because of the properties of physics, right? So the higher bands of 5G are already enabling that. So now again, the 60 will take it forward with the going for the other frequency bands at higher ranges. So now, I mean, we saw that with this 5G, the beam index based, angle of arrival, angle of departure, right? So the more precise that is, right? So my angular resolution will be vastly improved. So for that, of course, I mean, 5G has set the pace with all this massive MIMO, and you have all kinds of beamforming techniques that are already in vogue, right? So now 6G will again take it forward. Now we are talking about techniques like X MIMO or extreme MIMO, right? Or even like if we go to this again sub terahertz, we are expecting a very high density antenna arrays. So which means we are actually going in the direction of higher and higher angular resolution will also be possible as we move from 5G to 6G. So even though not very popular yet, right, but otherwise, I mean, we expect some kind of a collaborative localization. It's not just between something happening between the terminal and the network, but by some kind of a collaboration between the terminals in the vicinity or terminals and network elements in the vicinity, can something more be done accurately? Well, it's possible, but probably not uh, widely discussed or used anywhere yet. Probably we may see that going forward in release 17 or release 18. The D2D based, some kind of positioning. Right? So we can expect the trend to continue in 6G, but we don't know that yet how popular that will be. All right. So, and for EG triaging, of course, I mean, we need a network densification. We need a lot more reference points, for us to make sense of the surroundings, especially for the terminals. So, which is also happening. I mean, you can see in the lot of demos happening, purely without needing any other, satellite or any other ecosystem. No beacons, no sensors. Purely by having multiple small cells in an indoor environment, the kind of accuracies achieved are kind of unbelievable. I mean, that's possible because of the network densification. Again, we can expect that to continue. So now the question basically, so then what else, right? So it looks like whatever is needed for accurate positioning, those techniques are already having a good kickstart with 5G itself. So what else is 6G adding except enhancing whatever those techniques are already available in 5G? So that's where two main factors come into picture. So first factor being, we all know, I mean, the reason why we went to cellular positioning or any other form of positioning is because satellites are not reachable everywhere, right? So especially all the indoor or skyscrapers or our typical urban environments, coverage is very bad. So now with millimeter wave, it has already gone worse, and it's going to worsen. I mean, as we go into higher bands. So that's where definitely, I mean, RIS, the reconfigurable intelligent surface, is being seen as a very, very promising, technology to ensure very high levels of coverage in spite of, higher frequency deployments. So that's one. We'll see a little bit more in the coming slides. And then lastly, we'll show it in an example also. The 6G is being touted as, an AI native network, right? It's an AI native. It's not an afterthought. So, so definitely, I mean, all the variables, the nonlinearity is coming up because of these various factors, are better being dealt using AI/ML techniques than using traditional model-based techniques. Probably we'll see an example in the coming slide. So with that thought, yeah. So this is one slide to just to give gist of RIS actually. I think again all of you would have heard this term already, whoever is associated with this area. So you'll set up some surfaces, randomly wherever there is a blockage. You'll try to have a reflecting surface to reach the blocked area. So in that sense, in fact, this shows the heat map. Without RIS, we have a simulator of an accurate 5G system, actually. So we can see actually a typical millimeter wave. Really, I mean, in terms of blockages, we are already seeing it's becoming unusable. With SINRs, as low as -30, -40 dB. So that's why definitely RIS is needed to overcome that. So which will improve the signal strengths on all those areas wherever the heat map is dull blue. I'm sure it will take it to orange or red, right? But here is another important thing actually. This is my view again. So as much as RIS can help localization, right? Because RIS provides a means to reach the blocked areas. Right? So that means terminals are now uh, getting access to the network, right? Based on which all the previous techniques, right? Whatever your angle, phase, delay, everything can be estimated, right? It's making that possible. So, okay, RIS is helping localization, but alternatively or conversely, localization is also needed for the success of RIS, because we all know that RIS is a reconfigurable interface, right? Like on what basis do I reconfigure, right? So that means it needs to know first its surroundings. Basically, it needs to know where the target users are, or where the intended recipients are, or where the other anchors are located. So accordingly, it needs to be reconfigured, right? So in that sense, I think it's going to be a two-way street where RIS will aid localization, but localization is actually necessary for the success of RIS. So that's one thought to hold on to. So yeah, then of course there are the challenges, because clearly all the techniques so far, like be it angle of arrival or TDOA, they all assume far field propagation. But for the first time, because if you are going to have an RIS surface somewhere in the vicinity or in an indoor environment, you are going to have some all kinds of near field localization problems, right? So the waveform design also needs to be taken care, because now you are trying to achieve a dual purpose, right? Uh, and of course, I mean, the channel modeling and estimation is going to be a lot tougher. So, which I think already some of the other researchers actually on the panel are already dealing with those challenges. So, I have probably an example of what we did at Samsung Bangalore, just to show that without actually doing anything, purely existing some kind of a wireless system, you take the raw RX signals, raw received signals, and try to apply machine learning techniques to solve problems like this, right? This is an example problem. I mean, this was a part of the ITU AML challenge last year, right? Wherein there is a 4x4 transmitter and a receiver, a regular Wi-Fi wireless LAN access points, but of course operating at 60 gig frequency, right? So without any involvement of any of the terminals, purely based on the received signal, can we find the number of people, and can we count the number of persons, right? So I'll not explain this probably due to the paucity of the time, but just I want to show you that purely applying the AML paradigms, right, by separating or segregating in the Doppler domain and in the angular domain, our Samsung researchers are able to, actually they won this contest under this category. They're able to achieve 99%, counting accuracy, as well as 99% localization accuracy, and you can see with a very good, resolutions. So which means again, this bodes well for the localization even in a passive way, right? For the network's own purposes or network centric use cases. So then very quickly, I mean, this is my conclusion slide. So so what's positive? I mean, what's going that, hey, localization is going to be a key factor for beyond 5G or going towards 6G. So what are those factors? Then to me, I mean, these are the three good reasons why we should actually have localization as a central theme for beyond 5G. Number one, you can say this paucity of spectrum, the good quality spectrum, a lot of chunks of it is actually being held by the radar, aviation, defense, all these kind of industries, and that is being used in a very, very inefficient manner. So presuming that spectrum can be actually available for a joint communication and sensing kind of a system, we can do much better. We can actually use it in a much more efficient way, while at the same time providing all the whatever localizing or positioning capabilities needed for the other industries. Then second, of course, it avoids maintaining two separate infras, right? I mean, I don't need to have two separate infras for positioning and one for communications. And then lastly, a lot of these beyond 5G use cases, actually, everything, not only the use cases, but also the enablers. As I mentioned, RIS, I briefly touched upon, actually need accurate sensing and localization to be successful. But on the flip side, I mean, what we need to be cautious, I mean, why localization may not be a centerpiece, right? So one, of course, there are going to be all the privacy and security concerns, especially, if the networks are going to have this kind of capabilities, which are commercial entities. I mean, is it acceptable, or what kind of, uh, security provisions will be standardized to avoid that? So all those will be challenges to address. And second, and most importantly, there are already several alternative technologies like LiDAR, for example, is already being used in many industries, right? And UWB is fast catching pace. It's actually, in fact, there is a FIRA standardization body, which is actually actively working on UWB based, fine ranging. So now all these techniques at the advance, and with the combination of legacy technologies, if they do the same things as intended by the, for all the advanced use cases, then the question comes, hey, why do we need to complicate the 6G system? And of course, lastly, the viability of 6G enablers itself, because we are seeing the difficulties with millimeter wave, right? So then the similar difficulties as they arise with say terahertz or RIS kind of enablers, that may actually put localization on the back foot. So with those thoughts, I'll end it here. Uh, Thank you very much. Thanks for your patient listening.
Um, Thank you very much, Ratnakar. Any questions from attendees? Thank you very much. And actually, it is very useful to touch upon the the localization being the theme of all the current evolving use cases like and scenarios of XR, VR, and V2X everywhere. That would be an important, and also a need to integrate it to make the radio interface more intelligent and maybe the environment aware. So for that, that emphasis was good. Okay, over to attendees. For any questions, you can type your questions in Q&A.
There are no question yet in the chat or Q&A tab. Okay, I think Krishna Shirohi sir tell excellent overview talk by Ratnakar Rao. So that is the compliment I think.
Thank you. Thanks, Krishna.
Okay.
So no more questions.
Yeah. Then probably Srinivas, you can take over and go to the next
Okay,
speaker.
thanks a
Thank
lot. Thanks again. And let's now move on to the next keynote on integrated communication and sensing from Hideaki from Nokia Bell Labs. And he's right now working as a senior specialist standardization in Nokia. He has around 22 years of experience in telecom automotive industries, including NTT Docomo. And he has been working in the mobile telecom standard since LTE on various working groups like working group 3, 2, and also he is part of the TSG plenary. Right now, he's an SA1 delegate from Nokia working on 3GPP release 19, which is a kind of next level of 5G advance, which will try to bridge something related to 6G. And also, his topic is also related to integrated sensing and communication. I think already as Ratnagar touched upon sensing, localization and sensing that getting integrated into communication becomes an essential way forward. It looks like, and he will touch upon making use of the existing cellular telecommunication system and integrating the sensing aspects into it, and also the potential use cases and latest findings on the technology building blocks which would enable this integration of sensing into the 5G advanced and 6G system. Welcome, Hideaki, and over to you.
Okay, so I hope that you can hear me. So, and first of all, so I'd like to thank so the session coordinators and also the chair and the co-chairs for organizing this wonderful sessions, and also thank you also for all of the keynote speakers and the panelists, and also um, I would like to thank so everyone who joining this session. So now I'm going to share my screen and hope that you can see my screen, I guess. Sorry, let me start to my presentation. I hope that you can see the full screen. So if not, please let me know. So first of all, today I'm going to present Nokia's envisioning on integrated communication and sensing. So here is the agenda for my presentation. At first, I will share Nokia's 6G vision and timeline. So then I will explain the overview of the integrated communication and sensing, and also the 3GPP standardization status. And then I will also look over the potential technology building blocks, and then finally concludes. So, um, so let me start by sharing what Nokia is envisioning for 6G. Since the mobile communication was enabled with analog world and generations were grown, so human, physical, and digital worlds were getting closer. And then what happens for the 6G? In the 6G era, Nokia, we expect that the digital, physical, and the human worlds will become far more integrated. So 6G will profoundly transform our world, and liberate our innate human potential in the process. So, moving beyond the voice, video, and the data communications supported by legacy generations, um, future applications in the sixth era will bring more intelligence and better control and new experience to our society. So, on wireless system design principles for for every generations up to 5G, so networks have traditionally been measured according to their speed, capacity, reliability, latency, scale, and also flexibility. So these were key design goals for 5G, the so-called EMVV, URLC, and massive MTC, as you know. So then for the 6C, so we expect that the 6C era will require a new architecture for a new set of values. We expect that these sustainability, digital inclusion, security, and privacy. So these are becoming the new key metrics for networking, as well as the traditional metrics. So um, s- so in this slide, so I will explain for further what to expect from 6C. So the traditional key values, such as capacity, throughput, reliability, and so on. So these are still critical dimensions for 6C, and we expect that these are further enhancements. Further enhancements are still needed for 6C. So in addition, we need to address zero carbon footprint network for sustainable future and also global connectivity for digital inclusion of all people over the world, and also network trustworthy and also the resiliency. So Nokia believes that these are the key value drivers for 6C and differentiated from legacy generations. And and we expect that the 6C will support evolutionary use cases from 5G and 5G advanced. So in addition, 6C will also support revolutionary use cases such as the holographic transmissions, broad-based digital twinning, and also the network with a sixth sense. So this is related to the sensing topic I'm going to present today. So on 6C technical enablers, so Nokia has identified six key technologies that will be vital components of future 6C networks. So network as a sensor is, of course, one of the key enablers, and also AI native AI interface, and also new spectrum technologies, security, trust and privacy, cognitive, automated, and specialized architectures, extreme connectivity. So Nokia has been extensively researching these areas, and our deliverables are public in the paper and also academic journals. So today I'm going to focus on the network as a sensor. So next, I will explain Nokia's view on 6C timeline. So standardization phase one will likely start from 2025, leading to the first 6C specification um, in 3P release 21 um, by 2028, and followed by commercial deployments around 2030. So meanwhile, we expect that the 5G will have enhanced by 5G Advanced, which will be key focus for CCP in these 18, 19, and onwards. And 5G Advanced will also empower commercial public and private networks starting in 2025. So next is the sensing overview and 3GPP status. At first, I will explain what the sensing is. So especially from the network point of view as a network vendor. So sensing is one of the big transformation we anticipate in the move to 6C networks. So in this network, radio signals transmit by base stations and user devices. So they don't just carry data. So those wireless propagation channels also become a source of situational information. So the network can compare received signals reflected of objectives against the original transmissions to gather information about those objects. And those received signals can tell us not just about the presence of an object, but it can also determine its type and shape, and its relative location and velocity, and even its material properties. So that's why we call it as network as a sensor from network viewpoints. Another key point is that the sensing service can be provided by in conjunction with the existing communication service via the same spectrum. So, for instance, sensing enables the health monitoring service at home, and also maybe sensing can be used for the logistics services for the industrial IoT purpose. And also, sensing could also be potentially used for the agriculture by monitoring environmental change that might affect the agricultural crops. So, so then I will explain the standardization status in 3PP. So as you may know, 3PP has been evolving 5G technologies since the first specification was published in 3P release 15. So this year, so in Q2, 3P completed release 17 standards. So now 3PP is working on release 18 standards. That is to be the first release for 5G Advanced. And meanwhile, 3GPP has also started stage 1 standardization for release 19 specifications. So stage 1 standardization includes service use cases, requirements, and also KPIs. So for integrated communication and sensing, so feasibility study has started in 3P SA1 working group since Q2 this year. So so um, so the feasibility study covers sensing use cases, requirements, and KPIs. So the stage one work, including sensing, is to be completed until Q3 next year. So I will share the sensing use cases agreed by the SA1 working group. So in fact, a wide variety of use cases is discussed and agreed up to now. So covering consumer scenarios and industrial scenarios. So, so first of all, at first, for factory IoT, AGV detection and tracking is considered for sensing. So AGV, automated guided vehicle, is used inside the factory for automation, together with factory workers. So the scenario is that for safety purpose, factory workers can receive an alert that AGV is approaching or coming into the same working space. So to detect whether AGV is approaching or not, for instance, base stations transmit sensing signal, and then the reflected signal from AGV is received by base station or UE. So then from the measurement data of sensing signals, network processes the measurement data and analyze whether AGV is approaching or not. Then the alerting information is delivered to the factory workers. And then so next scenario is UAV, uncrewed aerial vehicle, so which is drone. And so drone flight trajectory is tracked by sensing and provided for service providers using drone. So example is that the service providers using drone on the package delivery service by drone, and also um, collision avoidance among drones can also be supported by sensing. So sensing capability enables to track the drone locations. And so if drones are approaching closely, drone traffic management system controls drones' flight path to avoid the collisions. And and also, sensing can also be used for detecting drone intrusions into the restricted area. And also, there is also the consumer use cases, which is traffic monitoring. So, for instance, so whether a tourist spot is crowded or not, so it is detected by sensing. So the traffic monitoring information is provided for mapping application service, for instance, a Google Map. So when users search tourist spots, whether the area is crowded or not, it is also shown on the map. Okay, so then automotive use cases are also envisioned. For automotive maneuvering and navigation, so sensing can be used to detect objects surrounding the car or the pedestrian for safety purpose. And sensing can also be used for road safety at junction. So for instance, so sensing detects a pedestrian or car around junctions and allows them to avoid an accident. And next, so sensing can also be used for intrude detection in home, private premises, on highway, and also railway. So for instance, so when someone is intruding while homeowners are not present, then a warning message is delivered to homeowner and security service. And also, finally, so sensing can also be used for monitoring environment. So as I briefly explained, so for instance, the rainfall and also flood monitoring. So when these events are detected, so the warning information is delivered to the end users. So this is similar to the existing public warning message services. So then, and also health checking is also a potential use case. So sensing potentially enables to monitor humans' detailed motion, for instance, sleep status, respiratory rates, etc. And also localization, as presented by the previous speaker, is also agreed as one of the target sensing use cases in CPSL1. So the sensing result can be used for enabling, for instance, spatial localizations. So sensing can be regarded as one of the technical enablers for localizations. And finally, privacy protection is also addressed due to the fact that the sensing can potentially collect information of targets. So even though target is not connected to the network, and also there is no consent from the owner of the target object. So these use cases have been captured in 3GP SL1 Technical Report 22837, which is public in the 3GP server. And it is still working in progress, and more new use cases may be added in future 3P discussion. Okay, so then next I will share potential technology building blocks for sensing. And so this slide shows technology building blocks we Nokia is envisioning to enable sensing capability from the network side. So this figure assumes the mode of the sensing operation that the base station transmits sensing signals and same base station also receives the sensing signals reflected from the target object. So this type of operation is called as monostatic sensing, or in the radar technology, it is said as a monostatic radar. So um, so first of all, so we expect that the new method of channel modeling needs to be investigated. So due to the characteristics that the communication between base station and UE and sensing between sensor node and the target node is done over the same spectrum. So multimodality could be considered for channel modeling. And hybrid beamforming between communication and sensing could also be a key area to support two services jointly. Maybe especially for sensing. For instance, code book or beam management might be studied to meet uh, required sensing accuracy. And duplexing is also a key area, especially for the monostatic sensing. For instance, a full duplex, I mean that the simultaneous transmission and the reception of sensing signal. I think it is possible. So if base station has transmitter and the receiver, sorry, base station has transceiver and receiver separately. So it means that base station needs to be equipped with additional receiver, which would increase the cost. So if full duplex is not supported, maybe the sensing signal is transmitted and received by the same base station in a TDD manner. So in that case, maybe it needs to coexist with the communication channel. And also, AI machine learning training could also be um, leveraged to improve the accuracy of sensing results, and also how to support sensing capability from the protocol perspective of maybe a radio protocol and network protocol. And so the QoS for sensing, these aspects could also be a potential area to be studied. Um, then I will share some of Nokia's research deliverables. So, so this slide shows the processing overview of OFDM radar-based integrated communication and sensing as an example of one implementation. So, um, so these processing components are quite familiar with OFDM-based transceiver and receiver. So maybe key thing is that in the lower side block, so the received sensing signals and also the original uh, sensing signal is processed to derive the sensing data, and also it could be further be used for the AI machine learning training. So this slide shows an example how AI and machine learning training is leveraged for sensing with the use case of the a car, car parking space determinations. For instance, sensing results and the camera image are utilized to run self labels. For instance, in this case, so this radiation obtained via the sensing measurement, I think this is corresponding to uh, the case that only one car is parking in this area. So captured by the photograph. So by combining these scenarios and input as a training data for the machine learning system, um, we could improve the accuracy of detecting parking spot availability. So then, so this slide shows a proof of concept in our laboratory test bed with millimeter wave. So although I didn't explain the detail, but I would like to highlight that actually we are conducting the laboratory test using our 5G millimeter wave product for the prototyping sensing use cases. So then finally, let me conclude with some remarks. So Nokia envisions that 6C will liberate human potential inclusively and sustainably. So network as a sensor is one of the central pillars for 6C. And CGPP has started feasibility study on integrated communication and sensing for Release 19 standards. And Nokia has been driving the key technology research for full potential unleashed in 6C. So that concludes my presentation. So thank you for your listening.
Thank you. Thanks a lot, Hideaki, on this wonderful presentation at a high level covering the roadmap, key use cases, and the building blocks. and also the importance of this integrated communication and sensing for the 6G technology. So now let's wait for some questions. Yeah, we have received one question. So I'll just read it. Maybe Hideaki, you can. The sensing beam is shown being reflected from an object.
Mhm.
Is it possible that UV and reflecting object to be the same than separate as shown in the figure? Yeah.
Yeah, I think, yeah. So, in fact, yeah, so CGPSA1 is also discussing the potential use case that UV itself also transmits signals and also receives the signals. Maybe one potential example would be the automotive use cases. As you know that for the automotive use cases, so Sidelink is used for the VTX services. So um, so in that case, maybe sensing could also be used for the VTX services from the service use case point of view. But maybe from the technical point of view, I assume that there would be the similar technical challenge would be foreseen for the base station size. That of course that UE also needs to have a full duplex capability. So in order to receive the sensing signals simultaneously. Of course, yeah, we could also consider the TD-based approach to transmit and receive the signal. So in short, I would expect that the same scenario also expected from the UE side.
Okay. Thanks a lot. So I think, yeah, the answer could be, yeah, it is possible that the same UE can be a reflecting object and it also be an UE, right? That
Yeah. Yes.
capability is possible,
Yeah.
right? Okay. Thank you. And
So there is no more question. I can see some compliment in the chat tab. I guess we get some more.
There is one more question, Asif, from Krishna Siroi.
Yeah.
you can flash, yeah. So Hideaki, you can see that question, right?
Mm-hmm. So I mean, it's beyond 5G based sensing. So I think so. Yeah, so if yeah, so we could use that so the dedicated infrastructure and dedicated resources. Yeah, um, so I'm not quite sure whether there is a benefit, but yeah, I think that so one big benefit we are foreseeing is that um, so s- if the sensing capability is integrated into the existing the communication infrastructures. Of course, that the infrastructure can also be reused, and also the spectrum can also be reused. So I think that would be the key benefit here. So if the dedicated infrastructure and the spectrum is already available for the sensing service dedicatedly, yeah, of course, yeah. So we can also reuse the existing infrastructure as it is here.
Okay, thank you. There is another question. Yeah.
Yeah, I think this is a good question. Yeah, so you mean that so if I understand correctly, so ambient intelligence is something like uh, that. If I understand correctly, so this is related to the IoT uh, uh, IoT kind of service that, for instance, that the device that does not have um, a power supply that the device itself has a capability of back scattering the signals. Yeah. So I think that this so ambient intelligence and ambient IoT use case could also be relevant for the sensing services. And I assume that maybe the joint use case could also be consider that maybe that sensing could also be sensing service itself could also be provided by the other ambient devices here. Hope that yeah. So I understand your question correctly. Yeah.
There is one more question, I think. Yeah, that can be the last one. Uh, yeah.
Yes. Yeah. Good question. So yeah. So as you said, so joint sensing is also you're right that yeah yeah. So we need to allocate some shared spectrums for the sensing. Um, so in fact, so these are, I think these are key factor to study the feasibility for the joint communication and sensing. So in fact, for instance, from 3P standards point of view, so we are still discussing and the service use case and the requirements, and um, we haven't discussed the KPI from the technology point of view. But I assume that later, so when 3GPP and standardization will conduct the feasibility analysis from the technology point of view, I think this is definitely a key factor uh, to discuss what would be the potential overhead to support a joint communication and sensing. Yeah, thank you for your good question.
Yeah. Okay. Yeah, thanks for very interesting questions. Yeah, those also matters, right? When you tightly integrate or when you loosely integrate onto the communication system. But at least the loose, not tight integration is essential because we want to make use of the cellular infrastructure for many use cases. But when it becomes integrated, these aspects needs to be considered and evaluated. For example,
Yes,
if a reference signal can be used for communication plus sensing,
exactly.
then
Yeah,
the overhead could be less. Those
of course,
aspects should
exactly.
be touched
Yeah,
upon. Yeah.
yeah, I agree. Yeah,
Thanks a lot.
yes.
Thanks a lot for these questions, and we'll move to the last keynote session. So this keynote session would be is from Professor Arzat Alam, and he is currently an associate professor in IIT Bhilai, and he has obtained his master and PhD from IISc Bangalore. He has worked on many research, design, development, and standardization aspects of device and applications in the telecom domain. So now he will be talking about the intelligent reflecting surfaces. So I think that being considered, I think it's a different perspective that we still react to the wireless environment at the base station. Now wireless environment itself can be controlled, and a controlled wireless environment can be provided as a service. So that's a definitely a new perspective. So he would provide more insight on that wireless environment as service, and also some learning problems and approaches used in the existing literatures, and also the recent work on using machine learning on this field. Welcome, Professor Arzat Alam. Over to you.
Okay, thanks, Srinivasan. While I am sharing my screen, how much time do I have? Uh,
Yeah,
I
I think
think we
time.
are
Yeah,
running.
good. Let me
I
check.
can cut short. Yeah, I have three phases in the slides,
Maybe
so
yeah, you can. I think 1820 to until 1825 should be okay.
sure.
6:25. You have 20 minutes. Maybe we can manage. That would
Yeah, yeah. My talk itself is reconfigurable, so I'll runtime cut it short. Should be fine.
dynamically. Yeah.
Okay. So thanks for inviting and uh, delighted to be here sharing our work and whatever insight we have so far on this. I'm Arzat Kherani, and I'll start with an example of an industrial IoT setup. This is a very simplistic example, but let us consider an industrial IoT floor where there are many sensors and multiple wireless technologies are actually being used. Okay, from because sensor vendors are different, they have some lock-in with different technologies and so on. And what we know is that this different wireless technologies essentially have lots of intelligence at the sender and receiver to effectively take care of the channel impairments. That's basically the point behind having this kind of intelligence at the sender and receiver. Now, that increases the technology barrier, and the sensor manufacturers, whose key job is actually to manufacture sensors, they are forced to work with and choose the right wireless technology, so to say. So they kind of get logged into interoperability aspects, and so because of all those considerations, it becomes very difficult for smaller wireless technology providers to get into sensor and get their solutions seamlessly integrated with the sensors or sensor providers solutions, and that leads to possibly significant increase in the end device cost. So the one of the ideas is or thoughts is ki if we can control the channel and leave the end devices relatively dumb, not very dumb but relatively dumb, what can be achieved? So that is one approach of looking at it. And it turns out that so-called smart radio environments can be possibly achieved using what is called reconfigurable intelligent surface. So again, here the smart radio environment does not mean one technology. Reconfigurable intelligent surface does not mean one kind of hardware. So there are many solutions. There are many technologies which can achieve smart radio environment. One implementation of a smart radio environment is via this. Now, here I know that I'm trivializing this, but if I look at how this works, it essentially goes to our class 11, 12th physics, where we have different variable capacitors connected to a metasurface. A metasurface is basically a reflecting plate which reflects the impinging electromagnetic waves, and depending on the surface impedance, which is controlled via a variable capacitor. So on the right hand side, you see equivalent circuit of the variable capacitor, and then trivializing it, essentially what we get is just by changing the value of the capacitance of this entity, each individual element, we can achieve some variation in the reflection property or other properties, say delay properties of this surface, the way it acts upon an impinging electromagnetic wave. So that's a basic part. Now, if you look at it, when we have to apply this concept to a bigger environment, so think of a big industry floor, and there will be many such. So one small device is one small element is like lambda by 4 or lambda by 2 or lambda by 8 length. So that's pretty small. Tiny element is not going to, one tiny element is not going to make much change in the received signal to noise ratio at the receiver. So you need a very scaled version of the deployment, which means that there is a overall radio environment which has to be configured, and there is one controller. So that's this roughly is the kind of scenario that we are looking at. Think of one transmitter, one receiver for now. There's some possible RF obstacle, and the waves are to be taken somehow directed towards a receiver, a common receiver. There can be some other reflectors also. So in this environment, in achieving this risk and working uh, service for smart wireless environment, we need to uh, have some expertise in fabrication. So that is one challenge: fabrication of the RIS elements in devices or surfaces. Being able to control is a huge task, and I'll talk a bit about that also. Then estimation of the ongoing performance. So this will when I discuss this will also talk a bit about what Ratnakar had mentioned earlier. Positioning is required in this or not. So we'll just briefly touch upon that. And what are the standardization aspects around this? So as is a common thing with any new technology, there are many Ekantvadi Saptandha Purushas, and then all of them trying to make sense of the new technology. You can see this from statistics gathered from Google Scholar, 4,770 papers on reconfigurable intelligent surfaces. And if I go one step further and ask for joint kind of thing, Then there are almost 3,000 papers, which reminds most of us possibly of what happened in sensor network days. We were having all kinds of joint optimizations and all kinds of cooked up problems. So having this kind of Ekantwadi Saptant Purusha is not a bad thing. I mean, this is certainly this is not a statement on any group working on these things individually. It is the nature of the problem here. But what we have tried to do is, and so happens that we are not seven, we are eight here. So we started an effort towards coordinated thinking, and we have a project, joint project between 8 institutes right now, which is going on this particular topic. Here are the participants. Almost all are, I mean, all of them are having equal participation. Even though IIT Bhilai is leading this effort, all are equal in this, and this project is under Triple IT Comet Foundation. So when we started, we had nine institutes participating, but Ravi Panwar moved from Triple ITG Jabalpur to IIT BHU. So now we are left with eight. So in this setup, essentially what we have is the following. This is a system architecture, and this is what we think is will be the deployment model. There will be companies which will be providing this kind of risk hardware. Okay. So in our case, the risk hardware will be provided by IIT BHU in Jodhpur. They are the ones who are experts in those. Not everybody is expert in fabrication and RF design. So this will come from them. And they will also provide a risk specific controller. What I mean by this is that this hardware implementation will be very specific to the exact technology that they are going to use, right? And they only know how to control it. Whereas at a user level, what we are interested in is the behavior, the overall behavior that this surface is having on the impinging electromagnetic waves. That's all we care about, right? So there is a risk controller. You can think of the left hand side as the classical communication part, where the communication part puts a demand on the right side via a standardized interface. Okay. For example, the generic risk controller, which is led by IIT Indore right now, they will ask the risk hardware via their own specific controller. Provide me with this angle of reflection or provide me with this much of delay and so on. So there are many configurable parameters and controllable parameters. So we are also standardizing this activity. This is going on within TSDSI, standardization of this interface. And then there's a channel estimation part. So this is actual communication on a transmitter and a receiver, which is being led by Triple IT Bangalore and IIT Dhanbad. So overall, we have tried to come together. Uh, this In this activity, we expect that there will be a lot of ML in the risk controller algorithm. So this risk controller algorithm is here in the generic risk controller, okay, via the standardized interface coming towards the risk hardware. Another key point will be that this hopefully, if we are able to standardize this will be the first standard coming out of India on risk aspects. So we are very enthusiastic about it, and all are welcome. This is an open invitation. This is, after all, coming out of a national mission, and whatever we are developing is and will be available to anyone who wants to try it out. Advantages are that, I mean, you can develop your own algorithm using the standardized interfaces. You can try out your RIS implementations and or your algorithms on the test bed. You can. So we will be publishing kind of a application development document, which if you follow, you just provide us with a pluggable module, and that will run on our system, end-to-end system. Right. So the advantage is that your module is standard compliant from day one, and you can focus on, any researcher can focus on their own expertise without bothering about the associated infrastructure, because this is going to be a complicated setup doing an end-to-end testing. So you're more than welcome. All are more than welcome. So in the remaining 7 6 7 minutes, I'll try to. So even though I had two problems to share, I'll just restrict myself to one of those ML problems. And these are the work with Srijit from IIT Bhilai and some of our UG students. So first problem is very simple. I mean, the idea is very simple. It essentially is about how RIS operates. Again, I'm slightly trivializing it here, But let us see where, how far we can go with this model. So there's a transmitter here, and there's a receiver on the right hand side, and the transmission has, so there's some scatterers on the path, which, because of which you get multipath naturally, and you are intentionally or artificially introducing a reconfigurable intelligent surface, which adds one more path. Okay. Now we know that the total phase change in the signal will be dependent on the length of the path. We all know that, obviously. So there will be some fixed phase change because of this path from transmitter to this and this to the RX. Okay. That let us represent by phi c here. So the problem now of the controller that the controller will face is that it has to kind of optimize or find the best theta rays. So theta rays for our purposes right now, we are assuming that RIS is capable of providing a phase shift of the on the received signal. That's all. So a very simple model. Forget about the power for now. Okay. That also can be incorporated later, but and we have some solutions for that. But for now, just assume that theta rays is what we can control. So our objective is to find the best theta risk, which is configuration of the reconfigurable intelligence surface, based on which we, for a given theta I and theta I vector and phi c values, so that the receive power is maximized. So the receive power can be low basically because of destructive interference and so on. So if there are no equalization and those kind of things, please remember that we are trying to make the end devices relatively dumb here. Okay? So if this problem is well understood, then here is this approach. Uh, what we do is uh, there's a concept of code book in reconfigurable intelligent surfaces. So not all phase shifts, not all values of theta rays are possible in practice. Okay. So depending on the way that this has been implemented, there will be some restrictions. So let us call that a code book. So you are allowed to select the theta risk values only from a discrete set, which we will call a code book. A fancy term, but that's what it is for now. Okay. And here we have a transmitter at the origin and a receiver at 300 meters. And these results are from just numerical computation of this model. So there's nothing stochastic about this for now. The heat map shows the actual value of theta ris, the best configuration that is required if one RIS element, so we are talking only about one RIS element, not a complete RIS surface, if just one RIS element was present at that location. Okay. So in the top right figure, we are assuming that all the values of theta is possible, 0 to 2 pi. In the bottom, we are assuming that we are quantizing it to the nearest codebook value. Okay, so that's the quantizing part. So what we can do here is we can. I mean, there are many other ways also. So one approach that we tried out was if we just have the coordinates of the RIS element fed into a neural network, and the output is a classification problem. So this is a classification problem where the output is four values. So in these four values are basically the four elements of the code book. Four possible phase shifts that are allowed by that particular or achievable by that particular risk surface. Okay. So that's we can train this system. Another approach could be just do interpolation. Okay. So one thing you may observe here is the lambda kind of periodicity. So I think we were using 2.4 gigahertz frequency here. So you will see lambda by 4 or lambda by 2 kind of periodicity in the optimal configuration, which is natural because everything is deterministic in this. Right? So the optimal configuration in the phase changes just by lambda by 2 uh, kind of periodicity. So when because of this kind of periodicity, turns out that interpolation is not the best approach. Okay. So when we have to deploy this kind of system on field, what we would do is just go and do some measurements at different locations of the industrial flow, and then see if we can extrapolate that to all values or all locations of risk. So here by risk, by changing the location of risk is actually not physically changing the risk. It basically only means that we are changing the transmit receive pair. Right. So risk is fixed. In practice, risk will be fixed. Transmit receive pairs will be changing, but it's the same problem. Right? So one of the problems we were looking at was how much data is required for training if we want to achieve a good enough performance. Right? So it turns out, and I will I think try to stop here. I'm already past 16 minutes. So it turns out that if we use only 40% of the complete flow data from, let us say, 30% of the complete flow, so you have to do only RF mapping and optimization problem solution for 30% of the locations on the flow, you are uh, close to 85% of the best that you can get. Right? So this is a good enough performance for us. I mean, because you are just what you are doing is just a simple DNN. I'm sure that more advanced models can be arrived at, and there are many more experts on ML, so they can do much more. The key takeaway for us was that training such a model is, I mean, there is a feasibility. This is kind of a feasibility study. It looks promising. We can take it further from this point. So with that, I will stop here. Thank you.
Okay. Yeah. Thanks. Thanks a lot, Arzad. And on the insights onto the reflecting and also the how this basically this functionality works with your trivialized diagram that helps us to understand the concept very clearly. Yeah. Any questions? Let me. Yeah. There is a question. Is the standardized? Maybe you can flash. Yeah.
Yeah, so Uttara, we have this activity is going on within TSDSI right now. 3GPP does not have this activity right now in this with this scope, but we are. I think I'm not sure. I think Ericsson is also co-signee in that. As far as I remember, I'll have to check that. But this is a TSDSI activity, and the standards, I think within 5 or 6 months, we already have made some progress on what kind of interface is required and abstraction around it. Hopefully, within a couple of months or 3 4 months, the first draft will be in public domain.
Any other questions? Uh, Maybe I have some two questions. Maybe I think it's from my side. So is this interface would be the interface from the RIS to the last leg of the 3GPP radio architecture, which could be the RU, right? That's what you aim to, right?
No, so we are not restricting ourselves to 3GPP, first of all. So there's no need to limit ourselves to 3GPP. There's a controller, and so think of this as a DJRF kind of interface.
Okay, fine. Yeah, thanks. I think if there are no more questions, we can at least conclude the keynote session part of this whole session. Thanks a lot for all speakers providing an additional insights and perspective on these three new technical components and then their effect on shaping up the 3G, 6G radio interface and systems. Now I'll give back the control to Srinath. Or do we have a break for some time? Ronak? Okay.
Actually, as a break is not planned, but if you want, we can take a break. And we have now time left is 45 minutes with us now for the rest of the
Okay,
session.
then we can continue. Then I'll hand over to Srinath for kickstarting the panel discussion.
Yeah. Thank you, Srinivasa. So, yeah, I think the topics have been very interesting, and I hope it has been able to keep the audience, hooked to their seats. Yeah, I think we'll now have a panel discussion, like in a similar concept. So far, like we spoke a little bit more about the research now, like what are the opportunities and challenges. This will be the basic discussion of the panel. So our panel will have three of the keynote speakers, Professor Arzad Alam Kerani, Hideki San from Nokia, and then Ratnakara from Samsung. In addition, we have three more eminent panelists. Uh, Priyanka Dev from SEVIT, Professor Sandeep Chepuri from IIC, and Vinay Srivatsava from Reliance Jio. So, yeah, maybe I can just do a quick introduction to the. Yeah. So, Professor Sandeep Chipuri, yeah, he received his MSc degree in electrical engineering and PhD degree from Delft University of Technology. He was a postdoctoral researcher at the Delft University of Technology and then a visiting researcher at University of Minnesota, USA, and also a visiting lecturer at Aalto University, Finland. So he has held positions at Robert Bosch and also at IMEC. And currently is an assistant professor at the Department of ECE, IIC Bangalore. So welcome, Professor Sandeep Chepuri. Yeah. Uh, Ms. Priyanka De is a senior research engineer in CEBIT. She received her master's degree in electronics and communication from IIT Bhubaneswar. She represents CEBIT in RAN 1 TSTSI and ITU. She was also one of the recipients of the TSTSI Outstanding Technical Contributions Award 2021. So she's been very active in the TSTSI standardization aspects. Okay, so her interests are 5G and beyond topics, specifically intelligent reflecting surfaces, full duplexing, network controlled repeaters, etc. I'm happy to welcome Priyanka on the panel stage. Yeah. Vinay Srivatsava is from Reliance Jio Infocom. He is a researcher driving multiple studies at TSTSI, focused on research areas related to future generation technologies, spectrum studies, and standardization aspects. He is a general manager, Telecom Science Group at Reliance Jio Infocom, has 2 decades of telecom and experience. He ended his masters from IIT Roorkee. He has contributed to Indian and international standardization efforts at ITUR, 3GPP, 3TSTSA, and ORAN. He has been actively involved in modeling, simulation, implementation of various generations of cellular standards, working with multiple MNCs during his career. Some of his standards contributions include NAVIC, AHNS standardization work in 3GPP, and also ITOR draft report on future technology trends towards IMT 2030 and beyond. Welcome, Vinay Srivatsava, on the panel. I hope now I'll be passing on the baton to Srinivasan to moderate the panel. Thank you all, and hope you'll have a very rewarding panel session. Over to Srinivasan. Thank you.
Thanks, Srinath. Thanks. And as you said, I think we have the interesting panel combination. We have experts from industries, including network vendors and operators, and we have team from research experts. So we hope we'll get some good insight and perspective on from this panel discussion. So I would start on a topic specific because we have three topics: localization, sensing, and IRS. And each topic specific, I have some questions to start the panel discussion, then followed by some common questions to all panelists on the common theme, which would be common for all these technologies. So I would start with a question on this localization. I think from the presentation from Ratnagar, it's touched upon the localization seems to be an essential component on many of those existing 5G advanced and 6G use cases. But also, I would like to hear from Vinay on that. From what's an operator's perspective on the new scenarios which would require a better localization than what we have in release 18.
Yeah, thanks, Srinivasan. As you rightly pointed out, Mr. Ratnakar addressed this particular topic already in his presentation.
Uh, some of Before we go to the use cases and scenarios, I would just like to briefly touch down on two of the differentiators which the 6G localization is expected or envisioned to have as compared to the current positioning techniques in 5G and 5G advanced. Right, we all know that we that positioning started from a regulatory perspective, from public safety use cases, and then it has evolved into, machine level positioning, which has now also brought in latencies which are, on the rate of 10 milliseconds. uh, However, to figure out what is still lagging is interesting. Firstly, the positioning methods themselves, right? The positioning methods in current cellular generation technologies normally float around the time of arrival calculation at multiple base stations, right? And then the location server triangulates these locations to figure out approximate location of the UE. These are mostly RAD dependent uh, measurements, right? And then there are some non-RAD dependent measurements which are also, collated with these to approximate a better position, and these are normally done at the location server. So which brings in many multiple dependencies in terms of the accuracy, possible accuracy, right? Because the tight synchronization in timing across the base stations and the UE timing data needs to be taken into account. Also, this mostly serves more towards, because the positioning happens at the location server. It aids the application which wants the UE location. However, for the scenarios where the communication itself wants to use the layer one, right, wants to use the location, precise location of an active user, or sense a passive user, there you cannot use it, because there the latencies which are required or envisioned should be within 1 TTI, right? And those have not been enabled. Plus the other thing, a single radio transmitting and sensing like a radar, right, in a monostatic configuration is not something which any of the cellular technologies till now support, and this is something which is envisioned to be brought in by the next generation cellular technology. That is the localization we are looking at. Apart from that, a very important thing which is the positional integrity, right, which can be a key cornerstone to the public safety applications when we use position for life safety measures, for public health, and UAV flight tracking, these kind of things. We require trustworthiness, and that has not been brought into the positional jargon till now in cellular standardization, right? And integrity is basically, it's the measure of trust that can be placed in the correctness of the information which is supplied by the navigation systems. It is already in place for aviation sectors, right? And it has multiple use cases, right from the public safety to the legal decisions and economic transactions based on the position of a particular vehicle during an accident, to the insurance thereof, and multiple such things which the MNOs look forward to enable in future generation technologies. So these are some
Okay.
of the use cases apart from the ones, which we all have been hearing, the real time digital twins, right, which require the sensing at the location, and based on which certain decisions could be taken offline. The localization in manufacturing facilities to so that multiple robots or cobots could cooperate together. The UAV flight tracking, public safety still remains, right, in forms of V2X, traffic monitoring scenarios, even gesture recognition in VR systems. So these are some of the scenarios which we look forward to enable once we have this envisioned localization in place.
Yeah. Thanks, Vinay. Thanks a lot. I think you had also touched upon, not only touched upon the scenarios which require localization and also the challenges in that existing technologies. I think the one interesting point, maybe I would like to hear some more views from Ratnakar on, I think how this triangulation, if it has to be used for a physical layer quick processing, how that very quick or tight integration, do we have any aspects from the next generation perspective on that. So because he said something, if we want the layer one processing to be optimized, then this triangulation done at the low server may not be in time. So is there a way to have that tightly integrated at the layer one perspective? Any quick views, because that was a interesting challenge I had.
Yeah, I think Srinivasan, yeah, thank you. So maybe I'm thinking actually now split into two minds for this problem statement, right? Like one is whether it's a an IoT kind of a device or a regular consumer or a specialized use case, an XR kind of a device, right? It really depends on that, right?
Yeah, true. That's true.
Because if you're talking about an IoT prospect, for example, where typically we expect the terminals to be, what is this low power, low complexity devices, right? In fact, we're going towards this reduced capabilities, right?
Mm,
So then naturally it cannot do all that on the device. So in such
yeah.
cases, probably, in fact, that's where probably cheaper techniques or technologies like UWB are coming from there only. I mean, the cost they impose on the device are quite low, or probably they will rely on this edge computing. I mean, where they don't take that
Yeah, that.
computational load on the device. That's in the IoT parlance. Uh, but of course, now coming to say complex user devices, very highly capable flagships or whatever these XR devices, digital twin devices. So I'm sure they should have the on-device computational capability, and probably that's where the AI/ML techniques will come into play, where you need to simultaneously play with the multiple non-linearities. So that will make it computationally efficient than the traditional methods.
Okay, thank you. Thanks a lot. Maybe I'll pause. I'll move to next question. In case if any panelists would like to add some perspective to this question, please feel free to add. Maybe from Professor Arzat, Chepuri, Priyanka. Please feel free to maybe raise hand, or you can unmute and provide some additional perspective on this question. Okay, so I'll move to the next question. Yeah, I think it's also already you touched upon how when you try to do a localization and it's a low complexity devices, so how the energy efficiency as a main KPI plays a role, and what are all the techniques which would be more relevant for this low power IoT devices? Maybe I can start with Professor Arzad. Do you have any views on that? Having the localization for a low power IoT device, because most of the techniques would require the device to transmit something which will have an impact on the device power, or the device needs to do some computation based on those multiple signals. So, is there an optimized way of doing it for a low power device?
Okay, so I think when we are talking about low power device, my first impression, and I have not thought a lot about it, but I have worked on some things related to this, is the main constraint for low power device is how much, what fraction of time can it keep its RF front end on, and the scheduling aspects come into picture. Right? When is the pilot signal actually being transmitted? And then you start getting into all the clock drift and those kind of synchronization issues. So receive a self localization kind of solution in IoT or low power devices and low cost devices, I think is not a good idea. It would be more of the other way. So the infrastructure localizes of the end devices. That's my feeling when we it comes to low power devices.
Okay, thanks a lot. Anything more, Ratnakar would like to add on that? This interworking or an impact on the
Yeah,
energy efficiency for this localization.
yeah. Just wanted to second what Professor Azad mentioned. See, in any case, most of these devices where low power IoT devices are involved, right? So, be it whatever it can be, asset tracking or whatever, some kind of meters or whatever we are talking. So, they don't need really the terminal to localize itself. Typically, network collects those locations, estimates, and offers it as a service probably for the actual application driving it. So in that sense, most of it will be happening on the network or on the edge. I mean, so the devices will not have much to do about the localization.
Right, right. Yeah, well, okay. The device may need to only do the transmission of those signals for that purpose, right?
And
Okay.
Srinivasan, if I may
Yeah, yeah,
add
sure.
here, right? The proximity sensing, right, or proximity localization, which is already being discussed in 3GPP reality, is something which takes care of such scenarios, right? We are extending the RFID sensing for such kind of low power devices to a slightly higher range, based on the cellular systems.
Okay, yeah, that could be a one on these lines, right? Yeah. Okay, then maybe I will now switch to the sensing, integrated communication and sensing topic. I think this point was also raised into the Q&A. As we have existing sensing device technology already available, what is the key motivation and driver to integrate it into the communication system, other than making use of the cellular infrastructure for sensing purpose? How do we see that integrated capability becoming more important? Yeah, I can start with Vinay, and then maybe Hideaki can add his views. Later, others can add.
Yeah, right. One thing which we have to understand is the small difference between localization and sensing, right? As I understand, localization is more about what we call positioning today, where you are trying to figure out the precise position of an active user, right? However, sensing is more towards the radar parlance, where you are trying to figure out the position of a passive device or an object, or as we said, the environmental things and rainfall, and it's a whole gamut of things. Sensing is something which is very very large in perspective as compared to localization. And so apart from integrating, right, and integration of course is the end goal, but may not come in the very first release of any SDO's 6G standard as such. We might have to live with hybrid approaches, wherein there would be scheduling between sensing and communication. Optimal scheduling, of course, because we don't want to end up spending a lot of energy towards sensing initially, because the communication network has to be green, one of the 6G objectives. And it will be intelligent, and then as the things evolve, and new enablers come into place, hopefully a common reference signals, and a common waveform for all. Probably there would be opportunities in future releases, or future further what do you call further releases of sixth generation, where they all can be integrated as such. So until then, there would be, they might, they might have to coexist together. And as you asked, right, and if they are not integrated, what's the motivation for sensing? There can be many, right? And as we already saw that, if there is a sensing mechanism which brings in integrity to the localization, that itself opens up use cases which were never possible to be addressed by the current positioning methods. The We will be able to enable the law, the economy, and then the use cases towards the trustworthiness, the health systems, and the even the traffic management, right, where the passive objects and obstructions have to be sensed, and the traffic updates, or the maps, for example, Google Map being one of the services, need to be updated proactively rather than based on the traffic congestion. All these things will be enabled, and hence sensing, it does stand as a strong candidature. In my opinion, the it's as we are going from 5G to 6G, it's not just about communication anymore. We have already enabled multiple verticals in 5G, and 6G will try to to enable the network of networks here. All the things will be coordinating with each other, helping to build a better ecosystem.
Yeah, thanks, Vinay. Hideaki, would you like to add something on this?
Yes, I think, yeah. So Bini made a good point that, so, for instance, that energy saving aspects. So rather than having the dedicated resources for the communication and also the sensing aspects, maybe so if the system is integrated, yeah, we can also optimize the energy saving aspects to save the powers. And also, in addition, yeah, I'm also thinking uh, there are the potential benefits that, for instance, that for the existing sensing infrastructure. That the one example is that that the camera is also used as one of the sensors. Recently, but that so if we try to install the cameras, maybe there might be a privacy aspects there for the customers some customers are quite nervous to install the cameras to be worried that they monitor explicitly. But but for the joint communication aspects, yes, we don't have to have such a privacy aspects. Of course, but as I explained, yeah, as that the sensing allows monitor someone's characteristics implicitly, so we need to have a private privacy mechanism. But anyway, I assume that there will also be some motivations even for the existing um, mechanism.
Okay, thanks a lot. I think as I also agree to Vinay that I think the starting point would be slightly a light interworking, light integration of sensing being available onto the same infrastructure, but slowly as a next step, it would become an integral component where maybe the radio interface could be aspects could be optimized based on the sensing information. I think that stepwise, yeah, would be the way forward. I think. Yeah, thanks. I think then let me switch to the IRS. Okay, I think yeah, I think as per my quick check, this simulation and modeling of IRS is really challenging, right? Because we assume a channel model and we provide a performance evaluation of a massive MIMO or XYZ. But how do you prove that we bring in some artificial reflecting interface surfaces into the system? And how do you model that and integrate and prove that? Because yeah, proving with the real things would be next level, but proving in a simulation would be needed. What are all the challenges and what is the maturity level of those channel models and simulations for this? So I would start with Priyanka and then Chepuri on this for the initial views. Maybe later Arzat can add to that.
Thanks, Srinivasan, and hello, everyone. Regarding this channel modeling for IRS, I can start with a very basic example. The basic difference between an IRS and the antenna elements that we use in today's communication systems is that the antenna elements that we are using today are basically active elements. I mean, we are pumping power into them, and they are transmitting the signals. But in case of IRS, it is a bit different because it's all about you have some passive elements, and whatever incident signal comes and falls on those passive elements are basically reflected from the IRS towards a particular direction. So basically the difference is in terms of the reflection that it is being able to achieve. So for example, if you consider a channel model, a very basic example of a 3GPP channel model, where the channel model consists of clusters in the system, right? And each cluster is supposed to reflect a certain number of rays towards the direction of the receiver. In my opinion, I think IRS, it can be considered as a kind of controlled cluster. By controlled cluster, I mean that when the reflections in the form of rays are they are being reflected from the reflector, you can basically model it based on a beamforming matrix. So that is the basis, like very similar to a beamforming matrix that you can have in case of an active antenna element or an active antenna array. You can have a passive beamforming matrix which will be kind of multiplied with the signal. I'm just using like a very simplified version, like you're just multiplying it with the uh, ray which is reaching the cluster, which is reaching your control cluster, or we are calling it the IRS, and it's getting reflected from the IRS. So I think that is like the first step towards the channel modeling of RIS. And apart from that, I would also like to touch upon like when you have an IRS in the system, when you're deploying an IRS node, then it is communicating with the base station if it has that communication capability. Apart from that, it can also communicate with the EVs, right? So the channel between the base station and the IRS will be different as compared to the channel between the RIS and the EV, because generally, if you see in case of repeaters and all, it's basically considered that the base station and the RIS, the channel, it's mostly like a line of sight. So the path loss and all those factors will be different. But when you compare it with the channel between the RIS and the EV, then again it might be consisting of non-line of sight as well as line of sight components, and based on that, it's obvious that your path loss and all those factors will also differ. So considering all these scenarios or all these factors, I think we need to develop the channel model for RIS. So I think, yeah, that's it from my side.
Thanks.
Thanks.
Yeah, thanks a lot. Yeah, thanks a lot on the stepwise challenges you have indicated on that. Uh, Over to Chepuri. What is your views on these challenges, or do we have something existing components available, as Priyanka indicated, to handle those and prove that okay, there is a performance X without IRS and performance improvement Y with IRS with the simulations already.
Mhm. Thanks, Srinivasan, and thanks, everyone here. Okay, so let me continue to build upon what Priyanka just mentioned. So, IRS itself is at TRL level 1, maybe at 2. That is where we stand today in terms of readiness. And there are different versions of RIS, reconfigurable intelligent surface or intelligent reflecting surface, two names that have been commonly coined. Uh, One is the main difference between an antenna array and RIS is that it is envisioned to be a passive screen in nature, which has many elements. And as a consequence, the fundamental limit that imposes on a system is that it cannot receive or decode anything. So, as far as channel sounding or CSI acquisition is concerned, you cannot do anything at the RIS itself. Now, what can be done is either at the base station or at the UE, or if you're using RIS for sensing itself, then you can measure echoes back at the radar receiver. Now, given that the channel sounding is fundamentally different when RIS comes into a picture. So all you can do is you can measure a cascaded channel. And the other fundamental limitation that it poses because of RIS being a passive element is uh, it imposes path loss that is much weaker, or the path strength is much weaker than the direct path. So you have a direct path between a transmitter and a receiver, and there is a virtual path that is introduced because of an RIS, and this virtual path will naturally be much weaker than the direct path. Now, given that whenever there is a direct path, RIS, unless we introduce some amplification, reflection type amplification into an RIS screen, there is not much you can benefit from RIS. Maybe very little in terms of the power that is received at the UE, but it is only useful or more useful whenever there is no direct path. So you can modify the propagation environment to introduce paths. So now, given this background, the channel sounding itself is difficult, and the gains are that okay, you can basically benefit when there is so when there is no direct path, there is nothing much we can do except for introducing virtual paths. Also, in terms of localization, now we can think of RIS as behaving like virtual anchor points. Without deploying a new base station, now you can generate geometric delays that you would normally introduce by placing different anchor points, like what we do with GPS, where satellite positions are different, and or you can think of base stations that are geographically separated. But now you can think of passive RIS screens. So coming back to channel modeling, again, so TRL level 1 or 2, the deployments or the fabrications that I have seen are there is no uniform uh, 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 screen that has been fabricated. There are different versions. One that we also have at IAC. I've seen many other versions also abroad. They're not uniform, and all of these are predominantly currently working at 2.4 gigahertz, and a few of them are designed to work at millimeter wave bands. So there's no uniform hardware as such to start with channel sounding. So we are in a very nascent stage as far as RIS is concerned. And what is the other challenge? What will be the front haul link between a base station and an RIS? So that is also something that we'll have to figure out. How do you? It's a very nice concept, which works in practice with all the little implementations that we have seen. But how do we now transmit signals from base station to RIS? So what will be that control link? What is the capacity of that control link? That itself is challenging. And so, yeah, those are my initial thoughts at this point.
Thanks a lot. Thanks a lot, Chipuri. Yeah, I think this is good insight. I think what are all the key challenges? Like as you said, the backhaul and the interface from RIS to the base station and that model and the fabric and how that plays a role in the reflection. So those are all the key challenges as you indicated. And also you also given some bonus information that this reflecting surfaces can be used for a triangulation in a different way. That's a new thought actually. A good point on that. And maybe Arza, would you like to give some concluding remark on these two views? Because you have a team already, I think you have marked that your team already working on this channel modeling related to RAS.
Yeah. So, there are three points that I want to bring up. First of all, a summary answer to your question is that no, there is no uh, good channel simulator available for this. There are in pockets few attempts are available. For example, Turkish group has SimRace and others also have. We also attempted some, and most of these are equation based or 3GPP model based. So they are the key thing missing in most of these models or simulators is the following. They are good in modeling the UE to RIS channel and the RIS to the receiver channel, the TX to RIS and RIS to the receiver. But the abstraction levels for RIS itself are not available at a mature level. And that is what I think Sundar Chipuri was saying, and I completely agree with his point that we can think of RIS, at least from fabrication point of view, as at TRL level 1 and 1 or 2, and then the abstraction is something which is not available right now. Because this abstraction will affect the channel model itself. So whatever we call channel is basically the cascade, as was used at the term that was used. So that will certainly affect, and it is not present yet. There are multiple ways of fabricating this, as I have already pointed out in our activity. Also, we are exploring at least two ways of doing that. And then we hope that in the standard, so one of the activities, one of the deliverables in the TSDSI work item is at least one level of abstraction of one kind of risk, at least. Okay? So that is certainly a work in progress. Second part that I want to bring here is the scalability. So as Chipuri already pointed out, one risk element is not going to make a significant impact. Think of a industrial floor if we are looking at IoT scenario. So I'm not looking a lot at the 3GPP and those kind of scenarios where we are talking about 5G, MBB kind of thing. I'm just talking about an enhanced or aiding the low cost end devices in an industrial floor, that kind of aspect. So there you will need a huge scale, huge number of such elements, and the issue is of scale there. So you are essentially going to, so when we fabricated, and I think Shipuri can give another figure. When we fabricated our wrist, we in a 1 feet by 1 feet board, we were able to fit in 150 elements. So, and you can imagine that in a big industry flow, 1 feet by 1 feet wrist will not do anything. Actually, it will not affect, it will not increase the SNR
to any significant level, right? Or so that's another thing. So this kind of simulators will require scale. By scale, I mean that each and every risk element will effectively be one endpoint in the 3GPP channel model correspondingly. So you can imagine the complexity of this. The third thing that we are realizing more and more is the interference caused by RIS. That is something that has to be incorporated in these models, and we have not seen. We have done some theoretical modeling of it. People are seeing. We after our work and around our work, we have seen other papers also coming out on the impact of interference if you control risk in a relatively bland manner and being myopic and greedy towards one transmit receive pair, it may have a bad impact at a network level. If you are talking about a network of transmit receive pairs, then it can have bad impact at the other place in the network. So especially it may not be the best thing to do. So but the impact of that on simulator is that the scale of simulator or the complexity of the simulator will be huge.
Yeah, thanks a lot. I think that also a good perspective, right? IRS brings some benefit, but also it can induce interference to somebody else, right? That should be modeled, as you mentioned. Okay, thanks a lot. So I will now switch to some basic question which is common to all these three technologies. So that would be open to all. I have a lot of questions in my mind, but I think we have uh, shortage in time. So let me switch to the common question. So how do we see the new spectrum requirements for these techniques for IRS, localization, and sensing? So let me start with I think maybe the new okay, the panelists who are joined for the panel discussion. I'll start with Vinay, Chepuri, and Priyanka, and maybe keynote speakers can add additional views. So the question is, how critical is the new spectrum for these three technologies?
Sure.
Vinay?
Uh, yeah, thanks, Srinivas. So, in general, sensing, as an integrated capability is of interest throughout the frequency range. Used by the mobile communication networks, starting as low as sub gigahertz, right? However, the new interest is mainly focused towards the sub terahertz band, and the reason being that it is enabled by the physical capabilities of the nature of communication which is used at such high frequencies, right? Also, the resolution of the sensing image that can be obtained varies with the frequencies. So, for frequencies around say 100 gigahertz, their typical bandwidths, it is possible to reach resolution below sub centimeter basically, right? At sub terahertz frequencies, the communication networks essentially employs beamforming for all transmitted signals, and beamforming is something which aids line of sight it depends on line of sight communication. And the nature of the channel is a very sparse matrix at such higher frequencies, and hence it's you can rely on what particular beam to do the sensing or localization very precisely. So hence this particular new technology which is of interest is more focused towards the higher spectrum of frequencies, right? Say millimeter wave frequencies, right, or as we call them sub terahertz.
Okay, thank you. Next, Chepuri, what would be your views? As I think when I said it would be required anyhow on the all throughout the spectrum, including the current NR spectrum range. But any specific thoughts on whether some technology components would work on a new spectrum better than the existing spectrums, kind of thing?
Mhm. Yeah. So, yeah, for enabling precise localization, more than the frequency itself, what is more important is the bandwidth that we allocate. Uh, and more the bandwidth, precise the localization accuracy that you would get. So that is a basic understanding. And the question that we should ask yourself is, why do we need to integrate communications and sensing? And if you again go to the typical bands that have been allocated to radar, so these are towards millimetric wave frequency bands, and then now uh, we are also trying to occupy those frequency bands for communications. So naturally, we should think of sharing the resources. It's not because that okay, the integration comes with a benefit, shared platform, etc. But now there is an implication because we are trying to now use the frequency bands that are useful for both. And coming back to RIS that I mentioned, so as we go towards higher frequency bands, the propagation loss becomes significant. So I cannot send wireless links far enough, because as we go higher frequencies, then naturally the waves die down much faster. So now a combination of RIS with integration and sensing becomes of paramount importance. Now I need to now think of relays at millimeter wave frequency bands with thousands of antenna elements might be power hungry. So can we think of passive devices that can act as repeaters? Now, yeah, that being said, I agree with Vinay that we require all these technologies either at FR1 or FR2, or even for wireless LAN Wi-Fi applications where sensing is important. Frequency, it comes with a limitation of regarding the allocation, but these technologies should be prepared for all the different frequency bands. So that's what I
Okay,
think.
okay, thank you. I think, yeah, definitely. I think any technology component should work on the existing frequency bands to minimize even the operator investment going for it. There should not be any mandatory need for it. If that is there, the technology component getting into the system is more predominant. Yeah, that's what I want to understand. Challenges in the existing frequency ranges to get this into, or if something will it work well on the new spectrum. Maybe the next to Priyanka. So what would be your insights, maybe like this IRS kind of components coming in? Do we see that works well in a new spectrum, or it's already good enough they're well integratable into the existing spectrum range itself?
Thanks, Srinivasan. So, with respect to IRS, I feel that yes, when we talk about this millimeter wave frequencies, right? So, suppose the IRS is being used for maybe for sensing purposes, or maybe for localization or positioning purposes, then it should be able to handle the millimeter wave frequencies on which the sensing or the localization is being done. That's a must. I mean, you're basically, if you're integrating all the three
Yeah,
technologies,
no,
then
right.
sharing of spectrum is something very important. And another example actually I wanted to touch upon with respect to this is especially for this right now in release 18, already there is a 3GPP study going on in this side link based positioning. So we have already started in integrating the, for example, the side link frequencies which is meant for side link communication, and integrating them with positioning, where the positioning reference signals are being sent on those frequencies and the positioning is being done, right? So the integration, I feel it has already started. And towards 6G, when we go more towards 6G, these and towards more higher frequencies like the sub terahertz band, there will be more integration in the sense like sensing, positioning, as well as IRS. I mean, I'll consider that as an enabling technology, but in terms of sensing and positioning, they'll be taken care of in those frequency bands where you get more bandwidths. And since you're having more bandwidths, it will be like useful, or you will get better positioning accuracies or sensing accuracies with respect to a particular technology. So yeah, so I
Yeah,
think
yeah.
that's my
Thank. Yeah, yeah.
perspective.
Thanks. I think, yeah, it's now clear. I think, yeah, it should be already available and working at least to a nominal extent into the existing ranges. But a new spectrum which comes with more capabilities, that would be more beneficial for this integration aspects. Yeah, and I would like to get views from keynote speakers. If anyone would like to add to this point on this spectrum question.
Yeah, yeah. Srinivasan, so Ratnakar, if I may add a few things.
Yeah,
See,
sure.
one is, while I mean, RIS is a very interesting or challenging research problem, and RIS based sensing and localization are the ways to go. So I'm thinking, one step backward, from a utilitarian point of view, is this integration a forced integration, or is there a real need? Right? That is what is the fundamental question which should be thought about, right? So,
True. True.
because I mean, I get a sense, just trying to play the devil's advocate here, right? So all the use cases of precise sensing for network as a sensor are predominantly from the network resource management point of view, right? Network operational efficiency point of view. So whereas for all real end user services, right? So today we talk of any indoor positioning scenario, right? So people have proven that sub-centimeter accuracy is possible actually with all the existing techniques. You take your Wi-Fi or Bluetooth, you would have a an accurate fingerprinting database, and then you apply AML on top of that. So people have shown that, right? And also technologies like UWB are also maturing in parallel, right? I mean, there are several use cases based on UW are also coming up. So in that sense, eventually, if this becomes, the 6G network to exist, it needs sensing capability. It's not that okay, there are some fantastic use cases which need this. That's why this needs to happen. So that is one dichotomy basically that needs to be clearly established yet, because like as the other panelists told, this is still at a TRL one research stage. So now coming to the spectrum point of view. So again, like we know that those of us who went through the 5G cycle, right? This the rush for the FR2, right? But finally, where we are seeing all the practical deployment problems and where FR1 becomes the preferred band of choice. So that's another point to keep in mind. Basically, what does this teaches us when we go towards either higher millimeter wave or sub-terahertz bands? So that's where if you see in the recent WRC or elsewhere, so the another very very popular band of focus for 6G is actually upper mid band, the 10 to 24 gigahertz range, and apply techniques like extreme MIMO to actually make that the choicest air interface for 6G. So which also will serve very well. I mean, because once we bring in the extreme MIMO paradigm where you have much more scaled up antenna arrays, so definitely all the benefits we are talking about in terms of precision of angle or position will accrue. But so there are alternatives at other spectrum bands. That's my view.
Yeah, thanks for this. Actually, the different perspective in the name of devil's advocate, but that is really good. Actually, yeah, we need to see from the other side. But okay, if we are trying to promote towards 6G, then we need to see slightly from a different angle, where we see that integration is essential kind of thing. But as you said, finally, which is more relevant, which the market needs, that will prevail, as you said exactly. And on the spectrum also, I think the mid that 7 to 20, that would be more beneficial for this integrated scenarios to work well. So I will have one last question to the keynotes, to start with the keynote speakers. uh, we have three technology components now described, and then so how do you see a role of these technologies in achieving the 6G system KPI? I assume the 6G system KPI is yet to be defined. In case if such one is defined in soon, how do you see all, is it all components essential to achieve that, or they are nice to have for a different use cases? So I just maybe a short perspective on that. What are all these are essential component to achieve required performance of 6G? I can start with Hideaki, Ratnakar, and Arzat. So maybe afterwards others can add. With that, we can close. We are already running short of time. Okay, we are already over time by 2-3 minutes. Yeah, this would be the last question.
Okay, thank you. So in short, I think these three technologies are essential component to meet the 6C KPI, as well as creating the new services here. So for instance, for IRS could also be the beneficial to improve the, for instance, traditional KPIs, increasing the capacity and the throughput, and also so as well as the IRS, also on the localization and also sensing also could be a key component and the integral part of the 6C technologies to create a new services. For instance, a metaverse-like service and also the telepresence services. For such services, sensing and final localization as well as IRC is a key component for. So that's why I think this should be the essential part and should be supported for the 6C from the beginning. Yeah, thank you.
Okay, thanks a lot, Hideaki. Yeah, as you said, you bring a good point. If a new scenarios becomes one of the KPI characteristics, then to achieve those KPIs, maybe all of them would be needed. So then over to Ratnakar. I think you have already
Yeah.
touched upon, right, whether I think as per you, may not be all of them may not be an essential component. It looks like, but just want to get your
Yeah, yeah.
views again.
Basically, as I said, even in the context of RIS, basically, I think they are mutually dependent. Like the kind of use cases we are talking about 6G and the enablers that we are talking about. So they actually need these capabilities
Definitely,
of
yeah.
precise sensing and localization, both the use cases as well as the enablers. So in that sense, if that has to happen, this capability has to be there in the system. So in that sense, I do think these are essential.
Thank you. Thanks for the precise answer. Then, Arzat, what would be your views on these becoming integral component and also becoming an essential component to achieve required performance of 6G?
Okay, so I think I was there in the first session today, and one of the basic questions was, "What are the KPIs of 6G?"
Yeah, that
So,
is not at there. I'm assuming something would come in, and yeah,
yes,
it is not at defined. That I know.
so
That's what I starting point. Yeah.
I, I'm not sure. I don't. I mean, I'm not in a right position to answer or even attempt that question. So it will be shooting in
Oh,
dark. So yeah, sorry for that.
okay. Yeah. Yeah. Yeah, okay, good. Yeah, actually, yeah, I think once you know that, I think it will all come when the 6G system defines properly. Because if the 6G system designs not touching upon this point, then they would not be a KPI revolving around it. But as others
So
said, if this
I mean,
becomes an essential component, then there could be a KPI
one
which should be
thing
relevant here.
one thing that can be talked about is the following, that I mean, we have seen a dot in 4G which was MBB, and then that evolved into a triangle in case of 5G, and possibly we are going to see a bigger polygon in 6G.
Right, right, yeah.
And then there are different KPIs. So, so if we are talking about different KPIs, we can always any solution will possibly. I mean, there will be no one solution fits all available. Obviously, as is in the case of 5G definition of triangle also. So will possibly be. I mean, the way we have seen uh, companies evolve their products is also that they started with something, marketing as something, and then later on it turned out to be addressing some other need, and then they started branding it in that manner, right? So I feel that a lot of that will be seen in the next decade.
Yeah, yeah, that's a good point. I think at least we need to visualize that polygon first. I think then KPI comes next, and then I think this question. But at least to get an initial views, yeah, this question. Any other views from other panelists, Vinay, Priyanka, and Chepuri? And with that, we will conclude our discussion and move to Q&A. I think there seems to be some questions.
So Srinivasan, if I'm,
Yeah, yeah, sure, sure, sure.
yeah,
Yeah,
yeah, thanks. So I just want to add some points with respect to IRS, which I thought of. Like, when we speak about IRS, it's basically like how it's going to affect the basic KPIs. For example, capacity or throughput or spectral efficiency. That depends on the use case, right? That depends on the scenario. For example, it can be used uh, as a enabler for coverage enhancement, right? So in that case, it's going to improve the coverage enhancement KPI. Or if it is used like in terms of throughput improvement, then it can be used in cases where you're basically concentrating the energy from the base station towards a particular direction so that the throughput gets improved. So it based on the scenario, your KPIs will be affected. But one very important thing, like I feel that should be kept in mind while talking about RIS, is the sustainability part that we talk about 6G, right? Because you can improve the coverage of a system by putting in more base stations or repeaters and all these existing nodes. But the difference is like the RIS, it's a passive device. It's going to consume minimum amount of power. That is what we are expecting, at least. So in terms of sustainability, I think I mean, as a node, since it's not using any kind of transmit power, it's basically a passive device. So the sustainability is something I think that should be considered in terms of KPIs when we are talking about RIS. Thanks.
Yeah, I think definitely. I think yeah, this is again an additional, a different perspective. So I think we all think of. I think even frankly speaking, when I write this question, I was thinking of the KPIs as throughput, spectral efficiency, X, Y, Z. I think definitely 6G will have some KPI defining the sustainability, and in that case, as you said, expanding in a different domains and different degrees of freedom will impact the sustainability, where IRS may may be a preferred one in that direction. Yeah, thanks a lot. And any, if we don't have any other questions, then let us get back to the Q&A. And maybe I think we can flash the question. Maybe we can get answers from the relevant or one or two people. Okay, let's, yeah, maybe I can start with Arzad. Would you like to answer? And maybe maybe we can get one more view from panelists. That way we can keep it short.
I mean, a good question. I don't have answer to the 5G relevance directly. What I am aware of is the issues, the field issues that people are facing in terms of, let us say, utility, smart meter deployment, and so on. So there is deployment in Hyderabad, which is for water meter. They are facing issues with LoRaWAN. So I feel that risks could be more useful there, as Priyanka was talking about uh, range expansion. So LoRaWAN, even though it operates at 866 megahertz and around that, people are observing, and it promises 5 kilometer range. But people in ISC and also in Hyderabad, they have observed a maximum range of 200 to 300 meters. So those are the places where it can be used, I think. But I'm not sure. I'm not very sure about 5G in terms of applicability of risk directly in that.
Yeah. Maybe anyone else from the panelist would like to add to this question?
Uh, I know. So Srinivasan, one of the interesting perspective for RIS is about enabling the RF communication at higher frequency ranges in two particular ways. One is that RIS can potentially break through the half wavelength limitation of the antenna spacing in the wireless communication, which is one field which people are looking at. And then as we see, right, the analog front end at higher millimeter waves is really challenging, and to do beamforming there is something which people are still exploring, going about. RIS can become an enabler for beamforming itself, at a much lower cost there, apart
Hmm.
from taking the advantage of cost and energy efficiencies.
Yeah, yeah, right. So I think, so from your point of view, it would be also relevant for 5G advanced onwards, right? Something like that.
It would be, certainly.
Definitely. Okay. Okay, thanks. I think we have short time. We can move to next question. Oh, I think this is a, oh, yes, it's from Vinay to Priyanka. Okay.
Okay, so actually, we have just started this channel model based simulations for RIS. So, how we started is basically we have taken the 3GPP channel model as a reference. For example, the 3D urban micro model, and we have tried to introduce RIS as a node in that model and see the behavior first. So like I mentioned, it can be modeled as a cluster in the whatever is already present in the 3GPP channel model, right? So that is the way we are actually trying to proceed towards it, that already whatever already existing channel model is there, and on top of that whether we can bring in some kind of enhancement so as to model RIS into that particular network as well. So that is how we are doing, proceeding towards the research for a channel model.
I see.
Okay.
Thanks.
Yeah.
Yeah, thanks, Priyanka. And I think there is one question: is no NOMA is practically feasible, but not sure it's in this context. If anyone would like to give some short answer, or we can take this question
Uh,
offline?
I can talk a bit about that. When Noma is being talked about, I think the discussion is also around successive interference cancellation. And in risks, we have found, so we have a paper in NCC last year, me and Srijit, and we have found that risk can be particularly useful in when used along with Noma. So we can discuss it offline, Dr. Bhupender. But yes, it's possible and it is useful in case of risk.
Okay, I think there is one question on standardization opportunities here. I I hope we are covered into the panel discussion on those standardization component. What are all the things are essential part of it? If anyone would like to add something more here.
Yeah. I think one of the standardization effort which also started apart from the one which Priyanka mentioned over the side link, right? In RAN 1 release 18, we have an item towards, study item towards the control channel design for intelligent repeaters. And RIS falls into this as a subcategory. You can envision, IRS being one of the intelligent repeaters. This work can potentially end up filling the gap which Dr. Chidri was pointing to, right, of forming the front hall or the interface from the base station uh, to these repeaters, intelligent repeaters in the form of RIS. And probably RIS would definitely need a sub UE kind of reception which the current generation repeaters or intelligent repeaters like Magic Box have to be able to sniff this control channel and act appropriately.
Okay,
And
thanks.
Dr. Arzad mentioned during the talk that there is a work item in TSDSI on RIS already.
Yeah, that's RIS controller interface. Yeah, right.
Computer interface. There is a
Yeah, but yeah, Vinay, that's a interesting point. But is that intelligent repeater that work item intent to define an open interface between the RAN and some those intelligent repeater?
Yeah, there will be a PDCCH kind of region, right, which would be specific towards the information being provided to intelligent repeaters, which will aid them to
Okay, okay.
form to do the beam forming thereafter rather than just repeating retelecasting.
Uh, Okay, so the intelligent repeater expected to be having some empty component to receive this PDCCH. It looks like, right?
Right.
Mobile termination. Okay, that's an interesting point. Thanks a lot for the discussion. Actually, bringing different perspective to the given question, and also we get as a bonus a lot of new insights and even the new concepts as part of the panel discussion. It's really interesting. Thanks for all your contribution. Maybe I'll then give it back to Mithal sir for concluding remarks.
now I think first Mr. Srinath will give some overall summary, and then I will give.
Okay, sorry. Yeah, maybe I'll give back to Srinath. You can take over.
Yeah, hi, thanks, Srinivasa. I think it's already a bit late, but just to conclude that I think this overall keynote plus panel was a very interesting set of discussions happened. So where models were presented, ideas were discussed. So it's something like okay, moving. What I see is like from theory to practice, where there is some modeling which is happening. There's also some activity which is happening on building up kind of prototypes, plus also like standardization fit. So it's a kind of all things brought in together, and we also have a very good mix of academicians and you know like the companies which are really at the forefront of research and contributing. So it's a very enriching kind of discussions that happened so far. Yeah, I would like to thank the keynote speakers and the panelists for all the insights, and definitely I think who have been through the whole session must have kind of been thinking some new ideas already which should, I think, whoever can possible can participate in either, like the academic research activity or the TSCSI forum to take this to the next level. Yeah, that's all I want to say. Thanks, and then I would ask Mitraji to kind of conclude on this. Thank you so much.
Thank you, Mr. Srinath. So I will be very short because we have already late. So uh, uh, I think the session, as already mentioned, has been so interesting and so engaging. And it was really interesting to hear Mr. Ratnakar Rao when he cleared the air about a lot of things about the jargons and the way they are used and how they are going to be, what are the, how they are required and how they can be used. So I think it was very eye-opening. Otherwise, localization sometimes, gives different kinds of meanings also. But he clarified, and Mr. Takahashi, very in a very concise manner, gave 6G value drivers and evolutionary use case with respect to the use cases for integrated communication and sensing, and the concept of network as a sensor. That was the concept he gave. And it is interesting to note that SA1 is already working in this area. And Professor Arzad gave very fundamentals of RIS in a very succinct manner, very simple manner, so that it's easy to comprehend for anybody. And but then the panel discussion really brought out the depths, the challenges, and new ideas and new thoughts and various possibilities. They were really brought out in the panel discussion, and the panelists who joined us, uh, in addition to the keynote speakers, they had also had lots of insights and the work, and we really had a very good mix of people here in the panel: academia, industry, R&D, researchers. Everybody was here. So I think uh, while discussion was happening, so I realized that okay, I think we put a very good panel together, and really we are thankful to all the keynote speakers and panelists to have agreed to our request, joining this, giving their time, and giving a lot of valuable insight, and making the session so engaging and interesting. Questions kept on coming, and they were answered. So I think overall we had a very good experience here in this, and probably had the session been longer, probably we could have discussed more. There were so many things and so much inquisitiveness. So in the end, I will like to thank once again our keynote speakers and panelists, our co-chairs, for conducting this wonderful session. And then I also thank our coordinators, Mr. Ronak Mishra, Asif, Jaskirat, and the whole secretariat team which was behind this arrangement, for providing all the support when we were doing arranging this panel, and co-chairs who were always on the, always they're present whenever we wanted to consult them. They were always present and guiding us. So thank you very much, and wish you all a very good evening, good night. I know it's very late for Mr. Takahashi, so very good night, and uh, to everybody. Thank you very much. We can close the session.
Thank you. Thank
Thank
you very
you.
much.
Thank you. Thank you all.
Thank you.
Thank
Bye.
you.
Bye.
Thank you. Bye bye.
Thank you, everyone.
Thank you very much.
Bye.
Thank you, everyone. I'm ending the session now. Thank you.
Thank you. Bye.